Okay, please, good morning to everybody. It's a very big pleasure for me to introduce today's speaker. Professor Leonardo Testi arrived in November at the University of Bologna as a full professor. Finally, we have the opportunity to listen to his talk, hopefully, because it's the first time that we try to have this talk here, but it's not solved. And Leonardo started his career in Florence, where he obtained the degree and the PhD. Then he moved for a first postdoc at Caltech. After that, he obtained a permanent position at INAP, at Planetary, where he stayed for a while. At a given point, he decided to move to ESO, and because of his interest for instruments, in particular, he had important roles in the commissioning of many of the instruments that ESO planned from 2007 to up to now, actually. In particular, let me remind the role that he had for ALMA. He was the scientific responsible for ALMA, and but it's not only in the ALMA range, but he covered also the scientific activities started from star formation, then we moved to the formation of planetary disk, and the main interest is the planet formation, and in particular the formation of our solar system. And this is the topic that he will present today. So let me give the floor to Leonardo.
Thank you very much, Laura. Thanks everyone for enduring the third attempt. Let's see whether we get to the end. So it's since a long time that I was putting it up that I completely forgot the abstract. So I don't know whether what I will tell will have any resemblance with the abstract. So I'll talk about the work that was done in our group, and also I will focus on what we want to do, because I thought that this would have been interesting also for you. And of course, it's a work done by many people from many different groups. I listed here some, in particular, the students that I've been having the pleasure to work with over the years when I was at ESO and now. Okay, some of you remember also the very old logos of our old Italian thing that started, in some sense, the adventure of this type of studies for me. Okay, so what's the topic? The topic is trying to understand the formation of the solar system, in general, the formation of planetary systems, and what is happening in this last years is that we are finally trying to get a picture in which we can compare our own solar system and the characteristics of our own solar system with exoplanets and the formation of exoplanets. So I think this is something that will develop even more in the future. Until now has been a sort of, there have been connections, obviously, but these have been the two very separate fields, the study of our own solar system and the formation of planets, with some connections over the past, but they mostly developed in parallel. So here are some of the characteristics of our own solar system in comparison with perhaps with other exoplanets and other things that I will get to discuss a little bit, and things that we would like to understand. The major points in our own solar system are the timeline for the formation of the solar system. We can trace it very precisely now in our own solar system. So this is an example of course, the ones online will not see where I'm pointing, so you will have to, I will try to be descriptive. The one on the graph on the lower left is actually showing a dating of meteoritic bodies in our own solar system. The oldest meteorites that we can trace, the carbonaceous chondrites, and it shows that the solids within the carbonaceous chondrites, which are undifferentiated meteorites, bodies in our own solar system. This is an important distinction. They formed, the oldest one, they formed more or less all at the same time, 4.5675 billion years ago, which, for astronomical point of view, it's a dating which is extremely precise, exactly. And the spread in age of these very old solids is extremely small, again, in our own in our own perspective. The spreads is only dated to be 10 to the 4 years, which is amazing if you think of it. And then other components in these differentiated meteorites have formed and aggregated towards with the rest over a time scale of 3 million years, roughly speaking. So this gray dashed thing is the dating of the calcium aluminum inclusions, this white oddly shaped thing, which are half a centimeter in size, roughly speaking. And the red and green and blue dots are actually the dating of the small spherical one, the chondrules that formed after the CAA and formed over a period of a few million years, as I said. So lifetime of this type of dust in our own solar system, so dust of the size 1 millimeter, 1 centimeter, few million years, okay? That's what we get from our own solar system. And then this disappeared from our own solar system. And the other important thing that we get from our own solar system is that in spite of how large it may seem to us, it's very small, so it's 30 AU. Beyond the orbit of Neptune, there are a lot of things, of little things, but they're very little. So they account for very little mass. It's a very sharp drop in terms of the mass in the solar system beyond 30 AU. So this is an important constraint, it's a sharp outer edge. And then the other thing is that since we are where we are on Earth, it's always interesting to figure out why Earth has the characteristics that it has. And Earth is within the habitable zone, obviously, but is within the snow line in our own solar system. So again, is another important constraint. When Earth formed, Earth must have formed in a dry environment. Dry meaning that there were no ices in the bodies that accumulated to form the rocky part of Earth, or there was very little. So this basically implies that the water and most of the volatiles of our atmosphere have an origin that is a mixed origin, most likely, partly from degassing of solids and partly from the delivery of material that was coming from outside the snow line. Okay? And this can be traced and connected with the chemical composition of the ices across the solar system. Okay? So this is also again an important thing. I mean, the small inset shows one of the typical diagrams that we look at. This one is for the hydrogen. So we look at the fraction of deuterium over hydrogen in the mean ocean water, for example, which is the thin blue line, and which is of course at the Earth position. And this value is a factor of 10 higher than you would expect for the normal interstellar medium and composition of the Sun and Jupiter. But on the other hand, is consistent with some of the ices in our own solar system, in particular in the ices that are in the comet, in the Jupiter comet, Jupiter family comets, sorry, Jupiter comet family comets, and in the main belt comets, and is lower again than the ratio that we observe in the very outer solar system. So it's tracing somehow a very specific region where it's coming from. Okay. And finally, of course, one of the interesting things that came out in the last few years is the comparison of our own solar system against the exoplanets. The diagram that I showed is actually not very updated. It's from 2015. So now there are more dots, but the basic point doesn't change. That's a typical diagram that is done in exoplanetary science. So the separation from the star against the planet mass. And in blue, you have the radial velocity detected planets. In red, the transit planets. And some planets, not many, but some are detected with both techniques, which allows to get very tight constraints. And you see that essentially the main families of planets that are observed in exoplanets are these three big clouds. The blue cloud, which are the Jupiters, let's say, the normal, regular Jupiters, if you want, that have a spread of separations between the star and the planet between 1 AU and several AU, like our own Jupiter. Is the Jupiter in green is our own solar system. So our Jupiter is at one of the edges of this cloud. These are, if you want, the ones that could be similar to our own solar system, if you disregard, obviously, that Jupiter at 1 AU destroy Earth. So is not exactly our own solar system, but these are the things that are more similar to our own solar system. And of course, we are at the moment a bit biased because our detection threshold more or less is here. So it's across the lower edge where Jupiter is. We are just starting to be able to measure Jupiters. And so we expect that this cloud of blue points to expand in this direction. But how much and how many will be our own solar system is quite unclear. Jupiter is the only one that the equivalent of Jupiter is the only exoplanet that we would be able to measure with current instruments, okay, in the current size. Then the other two families that somehow are very different from what we have in our solar system, and in some sense need to be explained when you think in terms of the formation and evolution of planetary systems, are the hot Jupiters, of course, the first, the easiest to detect in some sense, the Jupiters at very close separations from the star, and which are not many in the end. They are easy to detect, but they are not many. It's a few percent of the total systems. And then the big vast sea of the super Earth and mini Neptunes, which dominate actually the planet populations in the systems. Okay, and these are somehow a view of planet formation has to basically allow us to understand both this diversity of exoplanets and also our own solar system. Okay, so after this too long introduction, because I like to talk over myself, let's go on planet formation proper. So how this is the classical view of planet formation. The star forms out of the core in a molecular cloud. The core has typical sizes of about several tens of thousands of astronomical units, and has masses of the order of a few solar masses, typically. During the collapse, of course, there is conservation of angular momentum. So you form a disk at some point, you form a star, a central star, and a disk where most of the material is falling. The disk acts at the beginning of this lifetime of the system as a medium to basically admit matter onto the star. So matter flows through the disk, essentially, and angular momentum is dissipated outside. And then out of the material in the disk, in later stages, in principle, you can form planets. Planets happily form in the disk is dissipated, and you have a solar system or a planetary system, let's say. If you believe that this very simplified view, which was the view, say, from 10, 15 years ago, you plot out the lifetime of these disks. So basically, you look at how many young stars have hot dust around it, which is a very sensitive probe of whether there is material around the star or not. And you find that almost 100% of the stars have a disk when they are younger, so when they are, say, 1 million years or older. And then by 3, 5, 6 million years, most of these disks are dispersed. So this time scale, which was one of the main results of the Spitzer studies, Spitzer Space Telescope, and not Spitzer proper, Spitzer Space Telescope studies of star and planet formation, is in principle consistent with what I showed at the beginning of the timeline for the differentiated meteorites in our own solar system. So this is consistent. You have dust, which is warm around the star, possibly has grown. I will not go into grain growth. It is one of the things that I did a lot in the past. That coagulates, form maybe planetesimals, form the parent bodies of the meteorites. This is all consistent. Okay, it's all consistent, and so the idea that we had was that studying this disk, we can learn about planet formation, and this is one of the main things. So you look at this is a very famous image of a protoplanetary disk made by the Space Telescope in the Orion Nebula cluster. So of course the disk is what you don't see, and the size of the disk is typically 100 AU. The light of the star, you see it diffused on the surface of the disk. These are modeled and understood quite in detail, actually, in this phase. So this is the phase in which you have formed the star, as I was saying before. You don't have the envelope anymore. The disk is orbiting Keplerian around the star, and you have time in principle to accumulate dust and evolve the gas to form planets, if you want, in a time scale that is a few million years. Okay, these cartoons that comes at various times try to show what can happen within these disks. So you can have grain growth and the position of ices on the grains in the mid plane. The grain grow, accumulate, and perhaps form planetesimals. On the other side, you have the view of the gas that is a bit more complicated. I don't want to go into too many details. And then you have the other big important connection, which is the interaction with the star that basically provides the energy to the disk to evolve, essentially. And you can essentially trace all this observationally. What we have tried to do very much in the past 10 years is to characterize how much material there is in this disk, how it's distributed, what are the physical characteristics, and how these disks evolve with time. The idea that we were time meaning million of years, I think, trying to understand really whether how planet formation could work together. The key questions that one has in this area is what's the initial loading and evolution of the solids and volatiles in the disk, of course, where you put them, how much, what their characteristics, the physical conditions and the chemical inheritance from the core, from where from the cloud where they formed, the timeline and location of planet formation, where do planets form normally very close in, as where we see the mini Neptunes and hot Jupiters, or do they form in a very far region outside in a region even larger than our own solar system? So this was being explored, especially with the first high contrast images. The planet architectures, how many planets you form, how they are distributed, and so on. How common is the architecture of our own solar system, and the assembly of planetary atmospheres, how you trace the abundance, not only for Earth, as I was saying before, but also for the giant planets, how they accrete the gas through the disk, and what type of gas do they. And then the big questions that's always there, because one of the things that I've not discussed of our own solar system is that our own solar system, there are quite a lot of indications that has not formed in isolation, in the nice isolated picture that I showed at the beginning, but rather in a cluster environment. And so when you are in a cluster environment, you have the effects of other stars, and so it's unclear how this can affect your disk. So these are the things that we try to look at. Major breakthroughs in the last 5 to 10 years were done by the new instruments at the VLT and by ALM. And they basically allowed in this field 2 major areas of advances. The first area of advance is the surveys, large surveys of spectroscopic and with ALMA. So we started studying disk population, the properties of disk, not only of the brightest disks, but also of the entire disk populations, both in terms of the characteristics of the star and disk and the star disk interaction, but also in terms of the property of the disk. And the other big complement has been the high sensitivity and the high angular resolution, which obviously cannot be yet applied to full populations, but allowed to basically study what we call now in jargon, the substructures in disks, okay? Because we wanted to find planets which are point-like. We found mostly things that are not point-like, so they are not planets, so we call them substructures, as you will see in a moment. Okay, so major results out of these 2 things. The first thing, immediately after ALMA, we first immediately discovered, looking at these samples of disks, that none of them could have formed the solar system. Okay, so this was a bit disappointing at the beginning. This is a typical survey of disks in one of these young regions at 2 million years, but it doesn't change the picture very much. If you compare, we now looked essentially at all the star forming regions in the Gould belt, so within 200 parsecs of the sun, roughly speaking, and the result is always the same. If you look at the mass of dust that is present in this is a cumulative distribution of disks that have a mass more larger than this dust as in Earth masses. You see basically that less than 5% of the disk have more than 100 Earth masses of dust. And of course, 100 Earth masses of dust is the minimum amount to form something like our own solar system. So this means that either is super extremely rare to form our own solar system, or by the time we do these observations, so at 2 million years, essentially the core of the planets have already been formed. Okay? This was already the thing, so not only by 2 million years, but also by 1 million years. Okay, so in the very early stages. And this is also, you can look at this in very different ways. One way of looking at it, this one is a very statistical, just looking how many are massive enough. This one is looking as a function of stellar mass, because you may think, okay, you know, depending, a brown dwarf maybe forms not a solar system as large as our own. But then if you compare essentially the mass in exoplanetary system as a function of the host star, okay, so this is the host star and this is the total mass of solids, converting essentially the exoplanet masses into their solid core using Jupiter as an example. Note that Jupiter has roughly 30 Earth mass core. Then basically what you find is this blue line, okay? While if you look at the masses of dust in protoplanetary disk at 1 to 2 million years, you find the red distribution, which is at least one order of magnitude, let's say, below what is required to form these planets. So again, this is an indication that planets has already been formed. And again, you can look at this even in a different way. If you don't trust the conversion of exoplanet, a giant exoplanet into dust mass, you can look at nearby objects. So you look, for example, at TRAPPIST-1 or Proxima b, which are very low mass stars. They have rocky planets around them. And basically, they both have a few Earth masses in rocky planets. Okay. And if you look at the masses of dust around brown dwarf disks, you find that they are below this threshold. So there is a gap. This gap is real. This opened a huge debate in our field. Are you wrong in estimating the mass of dust? Because this is a big paradigm shift. Okay, planets cannot form in a few million years; they have to form before. So this was a huge paradigm shift. So we spent a lot of time in trying to understand whether we got the masses wrong of these disks, whether the conversion of from essentially flux, which is what you measure, radiation at millimeter wavelengths, and the amount of dust that is responsible for this emission is wrong. We spent a lot of time, and I think we now in the meantime we did some very cute stuff. So one of the things is really for nerd of molecules, which is measuring the mass in HD, because you cannot measure H2 because there's no dipolar, no permanent dipole. So you use HD and you measure it in the far infrared. And this is a very solid measurement of your disk mass once you correct for the 10⁻⁵ that you expect to be the abundance of deuterium, which has its own issues. And basically, but in any case, we have a few direct measurements of this mass, which is consistent with the other estimates that we were doing. And then we did, the other, the basic physics 1 experiment of measuring the self-gravity of the disk by the non-Keplerianity of the rotation of the gas around in the disk, and basically trying to do the differential measurements of the Keplerian mass that you have in the inner boundary of the disk, which is the star, and the Keplerian velocity that you have at the outer boundary of the disk, which is the star plus the disk. And this is a relatively solid measurements if you are able to do it, and if you are able to correct for other secondary effects. So, for example, the gas pressure gradient, the scale height of the gas, and so on and so forth. But assuming that you correct for all this, Again, we find that the measurements that we obtained and I showed before are correct within a factor of 2 to 3. This is still, I have to say that this is still an open discussion in the sense that, I mean, these measurements are not questioned, but they are a handful of disks. They are not the full population. They are the brightest and the more massive disks that can be probed this way. Okay, so this is an area in which there is still a lot of study, but I think it's generally accepted by now that the picture of planet formation slowly occurring over several million years has been revised. Okay, so the other thing that one tries to understand once believes that the mass is correct is whether the mass is distributed as you expect for this for the solar system. This is a plot that shows what is traditionally known as the minimum mass solar nebula. So basically, you take the bodies of our own solar system and you distribute them in a continuous fashion, in some sense, their mass in their orbit, and you try to estimate what is the mass distribution as a function of radius. So that's the famous Hayashi original measurement is in the dashed line. There are other estimates that you can do in different ways, but basically they are on a power law with two interesting exceptions that are quite interesting. The Martian asteroid deficit, which is an important aspect for the formation of a solar system, and the sharp outer edge of 30U that I already mentioned. Okay, so the assumption is now that there should be something like this. So we tried again to measure this in these disks, and this was one of the big efforts that we did in trying to model these ALMA observations in a more coherent way to try to understand the distribution of mass as a function of radius using proper disk models and proper modeling. If you focus on the plot on the right, which is the solar mass, roughly speaking, stars in these star-forming regions. This is a complete sample in this star-forming region. The black line is the minimum mass solar nebula, and the full green lines are what we measure, and the dashed line is our extrapolation, of course, within the resolution element, because we cannot resolve it below 20 AU yet in this type of observations, at least. And so basically, again, we see a similar thing as before, that in all these regions, there might be one disk in this range that could be consistent with having enough mass as our own solar system, but most of them has a deficit in the planet-forming region of at least 1 to 2 orders of magnitude. Okay, so again, it's confirming what I was saying before. Okay. Let me skip this because I don't want to waste too much time on this. I just want to point out one thing. One thing that we were doing also, we were trying to compare the observations of these disk populations. So the disk mass versus the mass accretion rates that basically traces how mass is redistributed into the disk and accretes onto the central star, and we compare it with the population synthesis models of planet formation. So population synthesis models of planet formation in their simple incarnation of the Bern, well, simple in quote, obviously, of the Bern group is basically starts from a disk at 0 age, let's say, and let it evolve viscously, like the alpha disk, normal alpha disk, and then planet formation occurs in the disk, and then modifies what you see in the disk. So basically, you have the models here in the lower graph in the color dots, essentially. The orange are disks without planets. So first of all, you note that most of the disks are without planets in these simulations, which is not what is observed in reality, because in reality, the statistics of exoplanets says that basically at least 80% of the stars need to have a deformed system, okay? But apart from this detail, the major features is that as the disk evolve, they go down in this track, and then they start to photoevaporate here. So they lose mass accretion rate, they go down in mass accretion rate at a sharp disk mass. That's edge here. And then when you start forming planets, you actually disconnect the outer disk, which is the mass reservoir, with the inner disk, because you put a planet in between, and this blocks the transfer of material. And this produces a drop in the mass accretion rate, because you don't put material from the outer disk into the inner disk anymore, okay? And so you expect to have this rain down of disk at large masses with low mass accretion rates. And these are two things that we don't observe, none of the two, okay? So this is an important thing. There is, of course, a big debate on whether our observations are sufficiently complete to see this or other things, but we are pretty convinced that at least we don't observe the amount of massive disks with low accretion rate that is predicted by the models. This is quite clear. We are not biased in that way, and this is a serious issue with the models and the way the models take time to build the planets and before dissipating the disk. Okay. Another way to look at these surveys, I mean, this is just to give you a flavor of all the surveys that we have, is to compare in this plot with the different evolutions. I don't want to go into this particular thing, except to tell you that if you compare with our own solar system, the undifferentiated planetesimals, so the ones that produce the meteorites that I showed at the beginning, that allow us to date our solar system, are in this time range, okay? Are in this time range between 1 and a few million years, roughly speaking, while we must have most of the planet formation happening in this green area, so at very young age for what I said. And if this is true, if this happens, this has a consequence on the evolution. The evolution of the disk is not so clean as is assumed in the other things. Another thing that is important and that we try to study is this outer edge of our own solar system as compared to disks. Most of the disks that are studied in detail are relatively large, but and measuring disk sizes is not trivial, but these are the first attempts to do this. So our own solar system is probably, or the original disk, probably had a radius of around, say, 50 astronomical units, roughly speaking, in dust, and no more than a factor of 2 in gas at the time of formation. So it should be in that area. So there are disks in that area. This is again a survey of one of these young star forming regions, radius of the disk in dust and ratio of the two radii. The problem is that the models, most of the models predict an evolution very different than what we see. So while our observations are more or less consistent with what we think our solar system was supposed to be, this is not consistent with actually our simple evolution models, okay? The simple evolution models are the big dots in this diagram. And even though the scale is different, you have to recognize that this is a logarithmic scale and this is a linear scale, okay? That's the difference between observations and models. Models always look good in logarithmic scale. You see that basically the issue that most models have is that the evolution of the differential evolution of dust and gas is extremely fast. So the dust tends to drift and concentrate in the inner region of the disk very fast, unless you stop it. And the way to stop it is with planet formation, okay? That creates essentially this stopping. Okay, so this is an ingredient that is missing in the models. We also looked at how these models compare when you look at the medians of the population. This is one of the many graphs that you can look at. Let's focus, for example, on this dot here. half a solar mass because it contains a lot of stars in all star-forming regions. This is the evolution of the mass accretion rates, which traces the transport of gas in the disk. And this is consistent with that dashed line that gives the indication of viscous transport. So this is okay, more or less. So it declines with time. If you didn't have planet formation, you would expect also the mass of the disk in dust to follow the same trend, which you don't see clearly in the dust data. Okay, so you see actually some quite peculiar behavior that the dust content seems to be relatively small when disks are young, and then has a peak around 2 million years, which is somewhat surprising in the simple models. Okay, so there are a lot of caveats with these measurements, but actually they may be related to this early planet formation. If you form planets in a disk of planetesimals that has formed planetesimals, then the planets and planetesimals interact, and the planetesimals are excited on eccentric orbits, so they tend to collide and produce a secondary generation of dust. Okay, this is a process that is known to happen, for example, in debris disks, so very evolved disks. But what we are basically saying is that this process might be very important also at very young age. And what we observe in terms of the dust in disks at 2 million years might actually be the result of this. These are examples of the production of dust as a function of age, and you see that you have this peak around between 1 and 1.5 million years. This is coincides obviously with the big growth of the planet when you create the atmosphere and form Jupiter, essentially. But you have also the formation when you have the rocky core, which is the first 500,000 year, essentially, of the group. And if you do these very simple models, you put them in this now is just a simplification in the sense that there are some sample runs of these models where we compare them with the observational data. You have in the dashed red line the original dust. Okay, the original dust that starts at the minimum mass solar nebula, so 100 Earth masses of dust, and forms planetesimals very quickly, so it disappears. But as soon as you start forming planets, which happens in the first 500,000 years, they start, then you have this secondary production of dust that creates this plateau, essentially in the dust content, and this perhaps increase in 2 million years. So again, this is consistent with the idea that these planets form very. So these protoplanetary disks, as I say, are not protoplanetary, but planet hosting disks, right? So planet formation has to be happening. Is there any evidence that this happens? Of course, you know that we have these substructures in disks. And so these have been suggested to be due to planets already from the beginning. So of course, the day this came out, okay, I remember still was in 2014, end of October, that we put out the press release. The following day, I called Simone Esposito and Adriano Fontana and asked them, okay, let's try to find the planet. And we tried with LBT. We invested a lot of time actually with the LBT, where we didn't find anything. We just put an upper limit at 3 Jupiter masses. Okay. So, okay, maybe this is a young, it's just dust. Maybe only the rocky cores are already producing this effect. So I said, okay, maybe this is still consistent. Then, as soon as this next disk we published on Physical Review Letter, because we basically not only we measured the gaps in the dust, but for the first time we measured the gaps in the gas. Okay. So the gas is the real density gaps in the disk. So this must be planets. So this time we called friends at Keck because the LBT ones were already irritated by our things. And of course we didn't detect anything there either. We didn't detect anything either, and with an upper limit of around a few Jupiter masses again, a couple of Jupiter masses. And then, you know, finally, okay, you have a big hole. The big hole must be due to something. We tried with sphere, and again, we didn't see nothing. So detecting planets is darn hard when you try to do it in the infrared in these young systems. And so far, there are many attempts there is one very confirmed case that we studied in detail because it has particularly massive planets, okay? This PDS 70b is estimated to be 10 Jupiter masses, very large. And there is another one that has been actually published a few months ago. And the reason why it's so difficult is that even if they carve a gap in the disk, there is still a lot of the disk atmosphere on top of it, and disk atmosphere with small dust grains. And so the extinction is still killing you in the infrared. Now here we did some estimates of, depending on the planet, where it's located, how massive it is, whether you can detect it or not. I'm still confident that with Eris, we will be able to detect them, but it's really borderline, and we need to go in the mid-infrared. In the sphere, in the near infrared is really impossible. So again, when you have a problem, you resort to the Star Wars method. No, I mean, if you don't see the planet in your chart, then you look at the gravity. And indeed, so this is an example of the first of these planets detected in these disks by indirect methods. So basically, this is the disk in the continuum, and these are channel maps of the gas velocity distribution. So it is orbiting around the star. So at +1 kilometers per second on this side, -1 kilometers per second on the other side, and that blip wiggle in the intensity distribution is actually created by the disturbance of the planet that disturbs the velocity field of the gas. Okay, this has been modeled in quite detail and has been quite convincing. So this was observed by eye. So with the bright student, we said, okay, no, we cannot do these things by eye, one disk at a time. It's impossible. So we have to do it systematically. So he built a machine, a war machinery, to basically analyze kinematic disturbances in disks that has a lot of byproducts. I mean, we can measure turbulence, scale height of the gas, self-gravity of the disk, but the goal was to detect these anomalies for the planets, and we tested it on that disk immediately, which we recovered as the planet. The X is the place to dig, obviously, as always. So the X, the green X, is where the planet is, and you see this in blue-red, the deviations from Keplerian, the local deviation from Keplerian distribution. But when you apply this to this disk, the same data that I showed before, so this same data, he applied this method and he found another planet. So he found another disturbance, this time in the inner region. So this time in the inner region and within one of the dust gaps. So we were so super excited by this, and he applied it to all disks that are available at this sensitivity, resolution, etc., which are 4, grand total of 4 at the moment. And basically, he found these were the 2 clearest candidates. There's a third candidate, which is quite clear. But these are difficult measurements. My point is that these are difficult measurements also for ALMA, and planets at 100 or 300 AU are rare. They are rare, and we know that they are rare also from the survey of exoplanets in nearby stars. Okay, so there is now a full program, large program of ALMA, ExoALMA, that is actually where we are doing these measurements, and the results are coming in the fall. We have a few detections, but very, very few. So the number of large planets, because you still measure Jupiter-sized planets, okay? The number of large planets in the outer regions of these disks is not very high. Okay, so this is one important point. Okay, so this one I wanted to, well, the thing that I wanted to stress here is the importance of the water snowline, as I said. This is important not only for the volatiles on Earth, but it's also important because growing planets in a fast way is not trivial. And the snow line, because it is needed, because they need to form very early. And the snow line is a place where you can develop some instabilities, because you are removing essentially the ice from the grains. So you accumulate grains because they slow down in the drift. And so it's easier to form planets. This is what is thought is the origin of Jupiter around 3 AU. Okay, that's connected to the snow line. That's why there is that cloud, this cloud of Jupiters around 1 to 3 AU, because that's the region where the snow line is. Okay, so of course detecting snow line is not easy, because observing water through the Earth atmosphere is not completely trivial, especially at high angular resolution, even for ALMA. But we managed. So we built the ALMA Band 5 receiver for this purpose already 5-6 years ago. It took us quite a bit, but finally, and we are hopefully going to publish soon, we detected the water directly, the main isotope of water from the inner regions of the disk. And we detected in 3 lines with the kinematics consistent with the disk. There you have some example. This is pretty high excitation still, so it's a few hundred Kelvin, because that's the binding energy of water into ice is of the order of 150. And the discussion that we are having at the moment is, where is the snow line? So we resolve it. Okay, so we resolve the sides. We resolve the sides, and the sides is more or less consistent with the first gap. So it's very suggestive that indeed the first gap is a planet that is forming at the snow line. But there are a number of issues. So the first issue is that the snow line in this system is expected to be closer in, not at that location. And the other issue is that most likely we are observing the water in the surface of the disk, not really on the midplane, because of optical depth. So this is work in progress, but it's very interesting also for the connection with other things of planet formation. Okay. So in the last 1 minute, I am trying to go through of what we are doing now and what we want to do. So where do we go forward? So of course, where and when planet form remains the question. We need to identify the planet location and follow the map with near infrared high contrast and spectroscopy. So one of the things that we are developing in collaboration with Lorenzo Pina and Arcetri is a new technique to do a combination of high contrast imaging, high dispersion spectroscopy in the thermal infrared, in order to be able to measure the spectra of the planets. And we have one master student here in Bologna who has taken the job of looking at this very strong-hearted guy. And this will be important for the brightest objects. We think we can do with the VLT and CRIRES Plus, but obviously this is taught for the ELT mostly in the future. And then, of course, we need to improve the understanding of gas and gas properties of these masses. One aspect that I want to say here is that we are focused on disks that host planets. So now we have to focus on younger systems, which are much more complicated to study, because there is the envelope that is collapsed, there is a lot of variations, all at the same time. Okay. Okay, and then we need to look at the chemical and physical conditions and the environment, which I did not have time to look. And I'll just flash few things here, just to show that we are doing some of these things. One of the important things is to try to study the different disk families. These families come, and here finally we are in Italy, so people will understand me. There are 3 families, and they are 33, 33, and 33. So in disks with the transition disks, D-sharp type, which are this one with huge disks with the rings, and the very compact tiny disks that nobody wants to observe because they seem boring, but clearly those are the ones that are probably the parent of something like our own solar system. So this tiny disk have a size which is expected to be the size of our own solar disk. We have tried to do with the student in Milano, still funded through IALMA, so many different disks. It's very good to have funding that don't require an immediate spending, so, as we know. So still funded out. Yeah, but nobody asked me. So, so we continued for 12 years with the IALMA obtaining a lot of results. Anyway, he's looking at this system. And of course, when you do at the detail, you discover that there is something else that is fastidious. So we have to look better in the radio to understand whether the emission in the radio is due to free or due to anomalous dust emission. This is a bit. Then the other thing is to look at, as I said, the disks in the process of formation, tracing the chemistry, the dust, and the mass loading of the disk. We have a number of things. One of the things that we are developing with EcoGal is a bloody machine that goes from simulations all the way to observations and comparison with observational data. This is not a trivial enterprise. We have a number of people working on this, including a student in Saclay. And then we are trying to trace the evolution of dust, because maybe dust does not evolve in the disks, maybe it evolves in the envelope. And so we are trying to trace this with a student at ISO from the outer region of the envelope down to the disk, discovering that indeed there is dust that is evolved already in the envelope. And the question is whether this comes from circulation from the disk through the outflow and in the envelope, or whether it is already evolved. Then the chemical evolution, complex molecules. This is, I would like you to appreciate that we are now able, this is work done by one master student here that has been, Jennifer Gianni, has gone for 3 months to ISO. This is the size of our own solar system. This is a protostar, and these are the emission in complex molecules that we are trying to resolve and to measure the temperature as a function of radius. And thanks to excellent ALMA data, she has been able to trace basically down to the orbits of the outer planets in our own solar system, the abundance of these complex molecules. So this is clearly something that it will be critical for the future. Okay, I'll skip this one, and I want to go to this thing, which is another exciting thing that we are trying with EcoGal, is basically improve on those population synthesis models of planet formation, starting from initial conditions that are not prescribed as isolated disks, but starting on initial conditions that come from models. These are 2 different model realization with of a disk in a turbulent collapse from the Saclay group. And basically we are using this simulation to basically have a simplified 1D prescription, because otherwise you cannot do population synthesis of the characteristics and their evolution of the young disks. And then we feed this to our disk population model, and we try to predict observations. And here you see some of the successes and faults that we have at the moment. As a function of time, you see that the gray, which are the observations, sometimes agree and sometimes don't really agree with our models. Of course, the missing ingredient is planet formation, so there are a lot of hopes that at some point we will be able to converge. And finally, and I think this is the last thing that I wanted to show, this is what we are trying to do to start observing disks in a bit more complicated environments than the solar neighborhood. And this is a news survey of the region around Trampler 14 in Carina. Carina is one of the closest major star-forming complexes in our galaxy. So it allows to observe disks in a cluster environment. But of course, if you want to obtain the same level of information that we have in our own nearby star-forming region, it requires a bit more work, both on the spectroscopy side and in the analysis. We have thousands of spectra. So Dominica, a student at ISO, has been doing the news data reduction and analysis. And Daeun Kang, who was a student, she graduated 2 weeks ago in Heidelberg, has developed a methodology based on conditional invertible neural networks to extract the parameters of all these spectra without having to fit one spectrum at a time. Okay, so this is the last slide. There are still open questions that remains. How to progress? Well, we will have a few people working here. So these are the little things that are coming in the next few years, and we will focus on some of these things that I mentioned. So trying to do the study of the, I go backwards because I like to go backwards, from exoplanet atmospheres and the link to the disk. To resolve the planet forming regions, this will be challenging. This requires a bit of instrumental development. That's why we are involved together with the colleagues here at OAS in the building of Plan 2, and then hopefully when ALMA will be upgraded, we will be able to really resolve the inner region of the disks. Then understanding the role of environment and following the chemical link of between the molecular clouds and the disks. Okay, on this I didn't spend much time, but we have a program of trying. EcoGal is about star and planet formation in the galactic environment. So I focused a lot on the planet formation on the small scale, but obviously we want to develop the link with the larger scale, the galaxy. So one of the things that we are trying to see is to put together also with Donatella, to try to put together what we know of the chemical evolution of the galaxy with what we can measure in different regions of the galaxy. Okay, I'll stop here because I think I already.
Hi, nice. And all programs you made a bit of a mistake.
Yeah, and I put it finally, as you might have seen.
With the near infrared, you cannot show them.
Yeah.
So I was thinking about the
Yeah.
So what about MS?
So yes, just to quickly, we have one of the follow-up of ExoAlma that we have approved, in fact, in this cycle, is to look for these planet candidates that we think we have, to try to find, to measure the planet itself in high contrast imaging with MIRI section. The problem of JWST still is always said like this, but it's the size. It's relatively small, so the diffraction figure is relatively large. Especially in the mid-infrared, and so basically you really need these planets that are a bit far out, so they are not the bulk of the population, because basically the fraction limit is of the order of 0.1, 0.2 seconds, and that is already too large. It's 50 AU. So it's large for the bulk of the population. But indeed, there are cases, and that's why it's there. The other thing is to do spectroscopy with JWST, the spectroscopy of the molecules in the inner disk, in the warm parts of that shape. So you have a lot of molecules in the thermal infrared, 5 to 10 microns, essentially. CO, water, and HCN. Yeah, exactly.
How your model for planet formation and disk evolution you compare to the actual conditions in star formations, since star forming regions are very active dynamically with lots of disturbances, and often there are also multiple systems which are forming.
No, that's a very good point, and in fact is the one that I skipped here. So one of the things that we are trying to do within EcoGal, in fact, is to have these very large simulations of not entire star forming region, but entire clumps, so that will form a complex system, complex dynamical systems, and try to trace the properties of the various disks and compare them with observations. So this is one example of this. This is a collapse of something like that. I don't remember whether it's 1,000 or 500 solar mass clump, which is turbulent and magnetized, of course. And we are comparing here some of the outcome. The dots are the sink particles. Around each sink there is a disk, most of them, not each, but most of them. And we try to compare the properties of these disks with observations. So this is the big difficulty here is that you need to do it properly. So that's why we have to develop this entire post-processing and then simulating observations and then comparing the things. The initial comparisons are here. So the gray are the shaded area are observations. And basically, this is not the figure that is best explains everything, but basically you get the right order of disk masses and radii. If you go like this, in our first example of running the full pipeline, the radii of the disk we can match within observation within a factor of 2, which is reasonably good, I would say. Even if the student is desperate, I think it's a great result. You know, this is the difference between students and the people less. But exactly. But the mass of the disk is a bit more complicated. It's the whole optical thing.
Given this, also the time evolution is different from the various parameters.
Yes, exactly. So one of the points is that in the simulation, of course, you know the age of each particle, and so that's. But in the observations, it's much more complicated. So in the observation, we use normally an average age of the region, and we compare this average age.
You can compare statistics.
Yeah, exactly. That's what we do. Because statistical comparison.
Monica, please.
If I understand correctly, to test the idea that planets have formed much earlier than originally, so you want to check disks without planets, but then you have to age date them. How do you?
So that's the
measure the
difficult.
age?
So basically, we found. This is debated, but I would claim that we find no disk without an evidence of planet, because indirectly. Because okay, directly is the planet itself is very hard, but what the next level is when we see these disturbances called the substructures. So substructure are present almost always, except in the very small disks. So the question is about the very small disk, whether they already have planets or not. I think they already have started forming planets because they still have, you know, otherwise, if you would take simply their evolution, the dust should have already been completely evolved. That's because dust evolution, so the drifting of the dust and the growth is an extremely fast process. So the fact that we do observe dust in retrospect after what we have learned in this lesson, the fact that we observe dust means that there is something that keeps the dust there or regenerates it. And the most likely candidate are planets in some sense for the disturbances that create collisions, or because they essentially disturb the gas distribution, and so you basically trap the dust. But this is the next frontier indeed, is to try to look at the very small disks and try to identify whether they have signs of planet formation already or not, and look at the very young disks and see in how many cases you have evidence of planets forming.
But the definition of very young is beyond measure.
Okay, if you want to go there, yes. In principle, also
Because you are talking of a few, a small
Less-
fraction
yeah.
of a million
So
years.
again, this is not dated by dating the star. Okay, so that's obviously it's already difficult for the million years. So this is done statistically again. So when you see these cases of disks embedded in a huge envelope that is collapsing, the time scale that you estimate for the envelope to disappear gives you the age of the system. So it's a statistical dynamical age for the system, which is uncertain.
I see a question online by Andrea Giannetti. Please, Andrea.
Ciao Leonardo. I wonder if you could comment on the impact of the environment on the disks and in general, because you mentioned it, but
Yeah, sorry.
passing.
The thing that we are looking at more specifically here is the effect of external photoevaporation. So basically here you have is a cluster with several O stars, and you have fields that are 10 to the 6, 10 to the 7 in the ultraviolet, larger than our diffuse interstellar radiation field. So with these fields, the outer regions of the protoplanetary disks are expected to be dissipated on timescales of the order of 1 to 3 million years. So these we have two clusters, one of 1 million years and one of 2 million years. And the idea is to measure and to check that effectively this process is happening on this timescale. So the outer disk is being removed essentially. So this is the specific test that we are doing here. Then obviously the other effect of being a cluster which is connected to our own solar system is well, the truncation of the outer disk, because photoevaporation might be the cause of having a small disk for our own solar system, but also the presence of some of the isotopes, the rare isotopes that we think were present in our own solar system at the beginning, like the if confirmed, I mean, this is very big if, the iron 60 or the argon, the aluminum 26 is more easy to produce, but if there are indications that maybe our solar system was polluted early on in its life. So this could be another effect that you have in a cluster.
And do you think there is any effect on the chemical composition? Because maybe if they are close to massive stars, they could be disturbed by the radiation field in other ways than the photoevaporation.
Yeah. You could have a different chemistry because of the high energy photons, indeed. But this I'm not a very expert of, and I don't think has been studied in systematic detail the effect that you might have on a disk. But definitely is a potential. There is a potential effect, indeed. Yeah.
Right, and the last thing, sorry, you showed some models with kind of environment with non-isolated disks, right? And do you see any mass accretion in the early stages? I mean, what's the, well, you do see some, but what can you quantify that?
That's every time I ask them, they say, yes, we have to rerun with tracer particles, which is, I think, a code way of saying that the way they do the simulation is not trivial to actually trace exactly what goes onto the disk and onto the sink particle. But that's one of the things that we are doing. So when I say here the simplified 1D prescription, basically what we are trying to do, we are trying to measure the mass loading of the disk. And this implies essentially the accretion as a function of age. So we are trying to trace how much material is going to, is not trivial because it's not obvious who is going onto the disk, who is going out, who is losing angular momentum, who is gaining until you have these tracer particles. But it's something that we are trying to do.
You have the very last urgent question by Daniel again.
You mentioned also compact disks, which are difficult to study since they are small. Which is the linear and depending on distance angular resolution we would need, and how many are within reach in the next future?
So, okay, so typically when I say small are less than 30 AU. Okay, because 30 AU, let's say in radius, because this is more or less our solar system and is more or less the angular resolution out of which you don't resolve in the surveys that we have so far. 30 AU, the nearest star-forming region are 160 and 50, let's say, parsecs. So you are talking of 30, 40, 60 million seconds, this sort of range. With ALMA, in principle, you have higher angular resolution. If you go, for example, at the high frequency, you go to 5 or 10 milliseconds. I wouldn't say easily because it's not an easy measurement. But the problem there is that the disks are completely optically thick, and so you don't see it. So the next steps are, in my view, SKA and ALMA low frequency with extended basements, in order to be able to probe the inner regions and the south. So who comes first? I'm happy, whatever it is. But you need, unfortunately, we need SKA, the high frequency bands, because if you go to the low frequency, then obviously the emission is different. It's not the dust anymore. So we need the high frequency SKA. That's why I say not always who comes first, because high frequency SKA needs a bit more time.
Okay. Thank you very much. Yes.
Okay,
Bye, everybody online.
aiuto.